Okay, continuing with chapter 3, we're going to be looking at the chain rule today, which is another very important rule that involves derivatives. So when we think about the chain rule, you want to think about composite functions. So a composite function is a function that's made up of two or more other functions. So like in this case here, we can see that we have one function that is x squared plus 4, and then we have this other function that is just the cube. So we would have x squared plus 4 that's being put into the function x to the third. So it would be like replacing the x with this function that's inside of that. So in order to be able to take the derivative, we have what's called the chain rule. Okay, that's going to let us do that. But just before we get to the actual derivatives, let's take a minute to kind of get used to the composite function notation. So this is saying, when you have it written like this is just saying that you're going to take the g function and put it into the f function. So here the g function is negative 3x. So I'm going to take that and I'm going to substitute the u in the place of the u. So I would have e to the negative 3x. So I replace that u with the g function. So that would be f of g of x. Okay. Here I'm going to take the f function and put it into the g function. So the f function is e to the u. So I'm going to put it in going in, and this should be u here. Okay, so I'm going to put the f of u function into g. So when I do that, I'm going to have negative 3e to the u. All right, we've looked at the power rule. Okay, so the power rule said that if we have x to the nth, we can bring that power down in front when we take the derivative and decrease the power by 1. That works fine as long as this is just x, but there's going to be some times where it's an actual function and not just x. So the way we're going to kind of extend that is, if we look at this, we've got u to the x raised to the nth power. So this is a function in and of itself. It's not just the variable x. So it does basically work the same way. The n comes down in front, and then we have the function, and we take the power and decrease it by 1. But the part that often gets forgotten is we have to take the derivative of whatever this inside function was that was part of the composition of those functions. Okay, so these are some simplified notation. So we've got n times u to the n minus 1 times u prime, n u to the n minus 1 du dx. So all of those are just different representations for the chain rule. All right, so let's say we're looking at this function here and we want to take the derivative. So it's the composition of this function inside of the function that raises it to the 4th power. So this lets us use the power rule with the chain rule. So the way we're going to do that is we're still going to bring this 4 down in front. We don't do anything to this part except recopy it. Just like we've done before, we decrease the power by 1. And then we have to take the derivative of that inside part. Okay, so we have to go back and take the derivative of this function that makes it a composite function. So it's going to be 4 times 3x plus 1 to the third, and then the derivative of that inside is just 3. So we end up with 12 times 3x plus 1 to the third. Do not multiply that 12 inside here, because when you have anything to the 2nd or 3rd or 4th power, it's almost like it puts up a wall here and protects it. You don't want to distribute into it. Okay, well, this is just another example. I'm going to bring that power down in front, recopy, keeping this exactly the same, decrease the power by 1, and then I'm going to take the derivative of this inside part. Okay, so that's going to be 3x squared. It's okay to combine these terms together here, but don't put them inside that parenthesis. So 21x to the 2nd, and then x to the 3rd plus 4 to the 6th power. Okay, if we have one like this, we could use the quotient rule, but it's going to be harder if we try to use the quotient rule. So there's some that it's going to be beneficial to do a rewrite of first. So I want to rewrite this as t squared plus t plus 4 to the negative 3 power. Okay, so this will make it easier to do by rewriting it. The rewrite is not the derivative itself, it's simply a rewrite of what we already had. So now if we look at the derivative of it, I can just bring that negative 3 down in front, recopy, keeping this exactly as it is. I'm going to take 1 from the power, so that makes it be a negative 4. And then I'm going to take the derivative of this inside part. So 2t plus 1. Okay. And because this is a negative exponent, if you want to bump it to the denominator so that it becomes a positive exponent for your final answer, that's fine. You're not going to lose points if you don't do that, but it does look a little bit nicer to do that. Okay, here's some for you to practice with. Okay, so our derivative here will bring the 3 down. I'm going to recopy, keeping that in the parentheses exactly as it is. Drop the power down by 1, and then take the derivative of the inside part. So that would be 15 times 5x plus 2 squared. And again, I can combine these together. I just don't want to combine them into that parenthesis. This one, same idea. Bring the 5 down in front. Drop the power by 1, and then follow that by the derivative of the inside, which would be 4x to the third. So combining these together, I'll have 20x to the third and leave this whole parenthesis to the 4th power alone. Okay, this one I would do a rewrite of first. So I'm going to rewrite it as t squared plus 4 to the negative 2. So that's just rewriting my original function. So now I'm going to take the derivative of it. So I'll have negative 2 times t squared plus 4, drop the power down by 1, so negative 3, and then take the derivative of the inside, so that's going to be 2t. Okay. So I can combine these together, so that would be negative 4t, and then since this is a negative exponent, I'm going to bump that to the denominator and make it a positive exponent. Okay, this one I'm going to do a rewrite before I take the derivative. And if you remember, the square root is the same thing as the 1/2 power. So if I take the derivative, that's going to be, I'll bring that 1/2 down. I'm going to decrease my power by 1, so it's going to be the negative 1/2. And then the derivative here, the derivative of 4 is 0. The derivative of negative w is negative 1. So I'm going to have negative 1 over 2. So the 2 is in the denominator. The negative 1's in the numerator. This is going to get bumped to the denominator because it's got a negative exponent, but it becomes a positive exponent once it bumps to the denominator. And you could even write it as negative 1 over 2 square root of 4 minus w if you want to get really fancy with it. Okay, so really this is just more practice with what we've been doing. So the derivative here is going to be, I'll bring the power down. So even though these are rational exponents, they still work the same way. If I take 1 away, that would be the 1/2 power. And then I'm going to multiply it by the derivative here, which would be 6x. So the 3 and the 6x are in the numerator. So that would be 18x times 3x squared plus 1 to the 1/2, and then that's over 2. So the 2 can divide into the 18. It cannot divide into this because since this is raised to a power, it's like that's protected with walls. Can't really get inside there to do any simplification. So 9x times 3x squared plus 1 to the 1/2. Okay, so this one is it is using the chain rule, but it's not using the power rule with that. So what we've got here is, I'm going to go back a slide or two. So what that tells me is that if I have two functions that are the composition of each one, you want to take the derivative of the outer one and evaluate it at the inner function, and then take the derivative of the inner function with that. Okay, so it sounds much more complicated than it really is. So on one like this, our outer function is the e to the x, and then this is our inner function. So what that tells us with that chain rule is the derivative of, we know the derivative of e to the x is in fact just e to the x. Okay, so the derivative here would be e to the same power, and then we're going to follow it by the derivative of this inner function here. So the derivative of that inner function is going to be 6x squared. So we have 6x squared, 6x squared e to the 2x to the third plus 5. Okay, so like take the derivative of the outer function and then the inner function. On one like this, if we're taking the derivative of our outer function is the natural log is the outer function. So if you remember, the derivative of ln of x is just 1 over x. Okay, so what happens is this is the natural log of some other function. So it's going to be 1 over, instead of x, it's going to be 1 over x squared minus 4x plus 2. And then I'm going to have to multiply it by the derivative of the inside function. And so that's going to be 2x minus 4. So we're going to have 2x minus 4 over x squared minus 4x plus 2. Okay, so a few to practice with here. The first one, this one is just using the power rule. So it'll be -5 times 2x to the third plus 4 to the -6, decreasing the power, and then follow it by the derivative here. So 6x. So it'll be -30x times 2x to the third plus 4 to the -6. And you can bump that to the denominator. So -30 over 2x to the third plus 4 to the 6th. Here, when you take the derivative, another kind of approach to this is think of this as like e to the u, okay? So the derivative of this is actually e to the u times du dx, right? So that means if I've got e to some other function, then the derivative of it is going to be e to that same function, and then follow it by the derivative of that function, which would be 12x to the third. So I'll have 12x to the third e to the 3x to the fourth plus 5. All right, the last one here, if I'm going to take the derivative of this, if you want to think of this as your u, okay, so we're starting with the natural log of u. So by the chain rule, this would be 1 over u, because we know the natural log of x is 1 over x. So the natural log of u is 1 over u times du dx. Okay, so that means the derivative is going to be 1 over all of this. So 1 over the u times the derivative of that, which would be 2x plus 9. So we'll have 2x plus 9 over x squared plus 9x plus 4. And this kind of sums up what we've been talking about here. If it's a power rule, you bring the power down. You still got that inner function that you have to follow with the derivative of that inside function. Here, if you've got the natural log of some inside function, you do 1 over the whatever this is. So 1 over the function times the derivative of the function. Here, if you've got e to some function, it's going to be stay e to the function, but follow it by the derivative of that function. Okay, so on this one, if I was going to give the derivative of that, this would be another e to the u. So the derivative is going to be e to the u du dx. So it would be e to the 2x times the derivative of this, which is just 2. So 2e to the 2x. This one would be the natural log of u. So that derivative would be 1 over u du dx. So it'll be 1 over x squared plus 9 and then times 2x. So 2x over x squared plus 9. Okay, on this one, we've got a couple things going on. You have to kind of figure out which one is the predominant function here. And so here we have a function being raised to a power. So we're going to use the power rule to do this derivative. So the derivative for this one, I'm going to bring that 3 down in front. I'm going to recopy this function, decreasing my power by 1. So it's going to be coming to the second. And then I'm going to have to take the derivative of this inside part. So I'm going to kind of come over to the side just to think about this for a minute. If this is my function that I've got to take the derivative of, that derivative is going to be 1 over this, so 1 over that, times the derivative of this, which is e to the x. So it's going to be e to the x over 1 plus e to the x. So that's what's got to go here. I think it can be a little overwhelming because this is an example of kind of why it's called the chain rule, because it's not just always one additional derivative, because it was basically like 3 functions composed together on this one, and it made it much more complicated. But this would be our answer. Okay, this one, again, we've got a function raised to a power, so we're going to use the power rule. So we'll have 3. We're going to recopy this parenthesis, doing nothing to the parenthesis, decrease that power by 1, and now we're going to come in here and take the derivative of this inside part. Well, the derivative of 1 is 0, so that's easy. Here, the derivative of this would be e to the x squared times 2x. So I had to think about if I were to come down here and have this function that I needed to take the derivative of, that would be e to the u du dx, or e to the x squared times 2x, and that's where that's coming from. So it is kind of a chain link where you keep having to take derivatives of inside things. Okay, so you could combine some of this together. The 3 and the 2 would make a 6x e to the x squared, and then we'd have the 1 plus e to the x squared squared. All right, last ones to practice with. If we're finding the derivative of this one, this would be the natural log of u. So we're going to do 1 over u du dx. Okay, so my derivative then would be 1 over that inside function, that's our u, times the derivative of that inside function, so 3x squared plus 2. So I have 3x squared plus 2 over x to the third plus 2x. This one we've got e raised to a power, so the derivative of e to the power is going to be e to that same power times the derivative of that exponent there. Okay, so that means I'm going to have e to the 3x squared plus 2, and then I'm going to follow that by the derivative of this, which is just 6x. So 6x e to the 3x squared plus 2. And then the last one here, we've got a function raised to a power. So I'm going to use the power rule. I'm going to bring the 4 down in front, decrease the power by 1. Then I have to take the derivative of this inside part here. Okay, so if this is my function that I've got to take the derivative of, well, the 2 is easy, that's a 0. The derivative of this is going back to this rule, so it's going to be e to the negative x squared times negative 2x, okay, because that's the derivative of this. So it would be e to the negative x squared times negative 2x. And we could clean it up a little bit. The negative 2 and the 4 could combine to be -8. And then we're going to leave this parenthesis alone. That's to the third power. And I forgot my x here. There does need to be an x. And that should be all. So the chain rule can get fairly complicated, but just don't get overwhelmed by what it is you're asked to do. Like here, it's always okay if you want to go over to the side and just think, like, if this were the only function I was dealing with, how do I take the derivative of that? And that's what would go here. So actually, what would go here. So just be careful with that.